So we are at the transport layer. We finished an overview of the TCP protocol. Let's now dig into the details. But first, a few questions. Unlike UDP, TCP is a connection-oriented protocol. In other words, a connection has to be established before you can start sending data. And during this connection establishment, both sides can exchange and initiate state variables. For example, they can negotiate what is the maximum segment size that they want to use. They can also exchange their initial sequence numbers. Why this is happening, we will look at it shortly. We can also figure out what is the acknowledgement type that you want to employ, either selective ACK or cumulative acknowledgement. Apart from this, you can also allocate resources, for example, the buffer space. So for example, once the connection establishes, both sides, the sender and the receiver, are going to allocate some buffer space for the send buffer and the receive buffer. How much is actually allocated is a function of the operating system. So these numbers can range from 4 kilobytes all the way to megabytes. In fact, you can configure these. For example, in some Linux systems, this value is 8 kilobytes. So let's look at how a connection is established. Simple. If A wants to talk with B, it can send a connection request. B is going to acknowledge this connection via a connection grant. Then both A and B can start exchanging data. Simple, right? Wrong. Things are often never so easy in networks. Remember, we are operating over a best effort service where packets can get delayed, they can get reordered, so on and so forth. So there is always the danger of duplicates from earlier showing up. So view that as a hint and tell me what can potentially go wrong in connection setup. So here is the problem. Suppose you established a TCP connection with your bank, and before the actual data, you set connection request, connection grant, and then as part of this data, you're saying transfer 20 lakhs to some account X. Now, some of these packets could have gotten delayed and the sender would have retransmitted them. And it is quite possible that these retransmissions got delayed arbitrarily, and after this connection terminated, they are again appearing at the other end. So this connection request is a duplicate that is appearing at the bank server. So in response to this bank thought it was a new connection and sent a connection grant. And here you are wondering what the hell is happening? Why am I getting some response from the bank? And in the meantime, your previous packet came and there you go, you transferred another 20 lakhs to account X and your bank balance is now nil. You definitely don't want something like this to happen. So what is the solution? It's a bit tricky, but nonetheless, think of how you can solve this problem. Originally, the TCP implementations did exactly this, but then this problem arose and later they changed the implementation. So here is the solution. The famous three-way handshake of TCP. So this idea was proposed by Tomlinson. Suppose A wants to establish a connection with B, it is going to send this initial packet. This is the initial synchronization packet, and as part of this packet, it is going to tell B that I am going to use sequence number starting from X. Now in response to this packet, B is going to set the flags SYN and ACK, where it is also synchronizing with A and saying I am going to use sequence number Y, and it is acknowledging this particular packet by saying I want X plus 1. Now A has to acknowledge this packet, so it is again going to set the ACK field, and it is acknowledging this packet by saying I want Y plus 1, and it can potentially send data as part of this connection. By the way, this is not needed. You could decide not to send data. If you are sending the data, you are going to start that particular sequence number with X plus 1. So the takeaway from this is the use of these distinct sequence numbers, that is one, and the other is that you send a packet, the other guy acknowledges, and you acknowledge the other guy's packet. So this three-way handshake is very famous, the SYN, SYNAC and ACK. In fact, there are quite a few jokes on it. Let me just tell one. It's not a great joke, but nonetheless. So a TCP packet goes to a bar and says, "I want beer, please." The bartender asks, "You want beer?" And the TCP packet says, "Yes, beer, please." So this kind of captures the three-way handshake. Yeah, I know the joke isn't great, but I think you will remember the three-way handshake better given that I have said the joke. So how does this solve the problem? Let's look at it. Suppose there was an earlier transfer, and after this particular transfer, this duplicate happens to end up at the server. Now it doesn't know this is a duplicate. So it is now going to send a SYNAC and it is going to select some other sequence number. Earlier that sequence number was Y, now it has chosen Z, and it is going to acknowledge this particular sequence number. And now this other end will wonder, what is this? I've never even talked with the server again. So it is going to reset the connection while acknowledging this particular packet. So as a consequence of this, this connection will never be established. This is the more interesting case where you have both the SYN packet and this data packet duplicated. So in this particular case, let's see what happens. So again, when you receive this SYN packet, you are now going to ACK it with a new sequence number. And now the earlier connection packet has come about, and here you are confused. I send Z, why is this acknowledging Y? So something is wrong. So you are going to discard this packet and wait. In the meantime, the other end will see this packet, worry what is happening, and is going to send a reset packet, thereby aborting the connection. By the way, if this client were indeed not listening on that particular port, in other words, it closed that particular connection, in which case it is not going to send this packet. But even in this particular case, in order for the connection to complete, it needs this acknowledgement. As I said, it's a three-way handshake. It needs the third handshake from the other end, which it will never get, in which case it is going to again close the connection after waiting for some time. So let me spend a little bit more time on this initial sequence numbers. So when we were describing the sliding window protocol, we always started with a sequence number 0. Now the question is, why don't we just start with sequence number 0? It makes things a little bit less complex. As you saw here, this distinction could happen because these sequence numbers differed. So it's very important to use different sequence numbers for the different connections. So that way the segments from the different connections cannot get mixed up. Not only that, there is a security risk when using these sequence numbers that are predictable. Originally, when the TCP was being designed, this was the goal. So what they did was to use a clock to choose these initial sequence numbers. So this clock increments every 4 microseconds, and so these 32-bit sequence numbers were derived from this clock. And given that it is a 32-bit sequence number, how long will it take for the number to wrap around? Roughly 4 hours. By this time, the older packets would have definitely been removed from the network, because as I mentioned at the IP layer, these packets do have a time to live field. They are not going to live in the internet forever. But then this predictable initial sequence numbers were being used to launch security attacks. I will cover a little bit more of this as part of the quizzes. But the point to note is that this wasn't considered safe. So current implementations use random initial sequence numbers to circumvent the security threat. So this is with connection establishment. So what do you think of connection termination? You think this is easy? Well, there are always twists and turns with respect to networking protocols. So this also has a twist. Before I get there, let's spend a little bit of time on understanding what connection termination is. Suppose process A is talking with process B, and process A thinks it is done, so it is going to issue the close call. So this asymmetric release means you are now going to just shut down the socket, thereby preventing not only sending of the data but also receiving of the data from the other end. So in telephone analogy, this is like you're talking on the phone. You think you are done, so you just bang the phone down, even when the other person still wants to talk with you. This is no good. This leads to loss of data, not only of data that is in transit, but also if B still has some data to send, if you close the connection, you're going to miss out on this data. So what is desired is this symmetric release where you treat each connection as two separate unidirectional connections and each side has to be released separately. So in other words, in this particular case, when process A says closed, you will not be sending any more data, but you will still listen to data that is coming from the B side. And this symmetric release is a tricky business. So let me motivate this through this two-army problem. This is a very famous problem that is posed in the context of distributed systems. There is the blue army and then there is the red army, which is the enemy of this blue army. Now this blue army is split. One battalion is on top of one hill, the other battalion is on top of another hill, and this enemy is in the valley. So this enemy is rather large, so this attack from the blue army will succeed only if and only if both of them attack the enemy at the same time. If only one of them attacks, they'll get butchered. And here is the problem. Both Army 1 and Army 2 need to decide on when to attack this red army, for which they need to communicate, and the messenger who is going to communicate has to go through the valley to deliver this message to Army 2, and there is a danger that this messenger could be captured by this particular enemy. So what strategy should they adopt to ensure that they both attack the red army at the same time? So think about it. Well, there is no solution to this problem. Let me explain. Suppose this blue army sent a message, let me call it message 1, that says let's attack on Sunday at 9 a.m. After sending this message, do you think this army 1 can just go ahead and attack the red army on Sunday at 9 a.m.? No, right? What if this message was lost? In other words, that messenger got captured. Then army 1 would get butchered. So what it should do is when it is sending this message, it can say, please act. Let's suppose this message got through. Now this army 2 is going to say, okay, fine, let's attack. And it sent this particular message. Now do you think army 2 can just go ahead and attack this red army on Sunday at 9 a.m.? Definitely not. What if this message got lost? It knows that army 1 will attack only after it receives this particular message because it asked for an acknowledgement. So army 2 needs an acknowledgement from army 1. So it can just also say, please act. Now let's say army 1 received this particular message and it is saying, okay, fine, I received your message. This is an acknowledgement. Now, does this mean army 1 can just go ahead and attack? Well, no, because what if this message got lost? It knows that army 2 will attack only if this message reached it fine. Now you see what is happening? No matter how many messages you exchange, you cannot decide on when to attack. So what is its relevance to connection termination? Here it is. So if neither side is ready to disconnect, unless it is sure that the other side is ready to disconnect will never happen. So this is a bit of a paradox. You really need to spend some time thinking about it to convince yourself that this is what is happening. So what is the solution then? Well, human lives are really not at stake here. While this is an unsolvable problem, you just follow a simple approach and make do with the consequences. So this is what happens in the implementation. So both sides follow a simple two-way handshake where if this process set close, it sends a finish packet, and once this acknowledgement comes, this side is no more going to send data, and similarly this side could continue sending data for some time, and when that particular process says close, you're going to send a fin which is going to acknowledge, and this side of the connection is also closed. By the way, in this process, you do take care through timeouts that you do retransmit the fin or the ACK so that this connection closes, but after a few number of retries, if it's still you're not able to get through, you're just going to close the connection. So this figure captures the TCP state diagram. It looks a bit complex, but it is really not. In this state diagram, this portion corresponds to the connection establishment and this portion corresponds to the connection termination. Another point to note is this blue line, which is being shown here, represents the server path, and this red line, which is shown here, represents the client path. So let's see what is happening. So both of them start with the closed state. The server starts listen, so that is why it now starts to listen, whereas the client connects to the server, so it calls the connect function. As a consequence of this connect function, the SYN packets get sent. So this representation where x/y, x is the cause, this is the response. So as a consequence of this, the server is now in the listen state and the client is in the SYN send state. Now when the server is listening, it is going to get a SYN packet. As a consequence of this, it is going to send the SYN plus ACK packet. So this comes when the client is in the SYN send state. So as a consequence of this, receiving the SYN plus ACK, it is going to send an ACK packet. From the client side, the three-way handshake has finished, so it is now going to get into the established connection state. And once this ACK reaches the server, it is also going to move from the SYN received to the established state. Once the connection is established, the data exchange begins. So this is where the sliding window protocol comes into play. We will see more of this later. Now if the client were to close the connection, so this issues the close command. As a consequence of this, the FIN packet gets sent and the client is now going to go to this FIN wait 1 state. And the server, when it receives this FIN packet, it is going to acknowledge that particular packet and it is going to go to close wait state. Now once this ACK has come, this is here, the client is now gone to FIN wait 2 state. So effectively the client side connection has closed at this particular stage because the client is in this FIN wait stage. Now still data exchange can potentially happen. Once the server issues the close command, then the server as a consequence of this is going to send the FIN packet. So this FIN arrives here at the client and as a consequence of this, the client is going to send the ACK. Once this ACK comes, it's not listed here. So this is the ACK. The server is also going to go to the closed connection. A point to note here is the client is not going to directly jump to the close. It is going to wait in this special state called time wait. So basically when you are terminating a connection, before you fully terminate the particular connection, that is go to the closed state, one side is going to wait in this time wait state. The reason for this, I'll get to it shortly. By the way, this state diagram doesn't capture all cases, and what I have shown via the blue and the red lines is the typical scenario. There are other transitions also as indicated here which can also be followed. I will leave it as an exercise for you to go through other transitions. So what is this time wait state? Basically, when you open a connection, after opening the connection, you are going to exchange data. So this is the data phase, and then you're going to terminate the connection. The use of time wait state is before you close the connection and thereby reuse the port numbers, you will wait in this time wait state for twice the maximum segment lifetime so that you can clear out all the older packets in the network and thereby preventing them from interfering with the new connection. So for example, you opened a connection, let me call this connection 1, between some source, destination, source, these are IP, and source port and the destination port. And you exchange some data, and let's say there is no time wait state. So as soon as you receive the FIN from the other side and sent an acknowledgement, you have just closed the connection. Now some of this data belonging to this connection could still be in the network because it was retransmitted or whatever. Now let's say the same endpoints corresponding to this reopened a new connection called connection 2 with the same bit. So this connection 2 is between the same source and destination and with the same source port and the destination port. Now if you don't wait for this time, what can happen is this older data can come as part of this connection 2, and this connection 2, typically the sequence numbers of that will not match this particular sequence number. As a consequence of this, you're going to abort this connection by sending the reset flag. So this is unnecessary work. So to prevent this particular case, as part of connection 1 itself, you wait in this time wait state till all this data disappears. Only then you free up that particular socket and the ports, thereby the second connection can be established. So when you're waiting in this time wait state, even if at the application layer you try to reopen the connection with this 4 tuple, you will get that bind failed. So this was mentioned as part of the socket programming tutorial also. Now how much time to wait in this time wait state is an implementation artifact. It can range from 30 seconds to 2 minutes. You can set it to a small value as well, but then you have to face this consequence of older packets interfering with the new connection. So there is this neat little command called netstat that lets you check the status of the connections, both TCP as well as UDP, and the state the TCP connection is in. So let's try that. So it is netstat -a lists out all the connections. Let me start out the regular netstat. So as you can see, one of these connections, which is to this 161 address, is in the time wait state, whereas the others here are in established state. So if I do -a, it's going to list a lot more. These are local processes. They're all in the listening state. I have one in the time wait state, some more in the time wait state now. Some are in the established state, some are in the listening state, and this also lists the UDP connections that are active on my computer. This refers to the IPv6 address. So there are some processes that are using the IPv6 address space. This you see as part of the TCP also. So here is the IPv6 address space. So to summarize, TCP is a connection-oriented protocol. This connection management is complicated by the fact that we are running over a best effort service model. We saw a specific problem arising out of these duplicates interfering with the new connection. We handle this via the three-way handshake. Making use of random initial sequence numbers also helps in this context. Connection termination is also a complex problem, but we went with a simple approach where we managed termination via a two-way handshake. We also looked at the TCP state diagram. Up ahead, we will see the sliding window in action in the established state.